level, station 1 or 2 or A, B, whatever. I don't know yet. I haven't got that all figured out. So anyways, y'all have had equipment talks, correct? Already in the class. So these are DC power supplies. I actually have quite a few more coming. As you'll find, a lot of process control equipment requires what's called an excitation voltage in order to work. We have a differential pressure transmitter at the bottom of this tank, and that's what's being displayed here is the measurement. So one of the things that I'm sure Dr. Hunter talked about in terms of, and this is something, a theme you'll see in every single experiment and any process control system for that matter. You have a measurement sensor that's measuring some input, right, that you want to control. You have some controller that is like the brain of the whole process control system. And then you have some final control element. In this case, it's a electronic proportionating valve that it receives a signal from the controller that then tells it how much to open up. Okay? And one thing that we're going to standardize in this lab is going to be 4 to 20 milliamp signals. And there's a couple of reasons for that. One is that's kind of the industry standard. When you have electronic equipment, they have different types of outputs. Differential pressure transducer has 0 to 100 millivolt output that is what's called ratiometric. In other words, it depends on the supply voltage on its output. Its output is dependent on that. So that's a 0 to 100 millivolt output. You have a stroke rate controller, and you saw these in the transport lab. And yesterday I was playing around and I actually got this and this to keep the level constant. I was going to demonstrate that today, but I didn't have enough time to get everything set up. So I was playing around with it yesterday, got it to work. It was pretty good. So now I know for distillation how to program it in LabVIEW so that it'll keep the levels constant in both the condensate receiver and the reboiler. So see, I learned something from this lab too. So you have your pressure transducer that then goes to this device. Based on that measurement, this device makes a control decision on how to change the output to the control valve. Now for the first part of this experiment, we're not going to be using this controller at all. You're going to be doing it manually, okay, with a DC power supply. So we can mimic sending a 4 to 20 milliamp signal to this control valve using a power supply. So I said, I'm going to provide you with wiring diagrams on all this stuff. Everything will be labeled in some way, so you'll need to understand and I haven't come up with a standardized way to label these things, so it may change a little bit. That's one reason why I wrote it in a pencil. But eventually we'll get some kind of standardized nomenclature for everything. We'll do it. So the first thing you need to understand is how these signals are flowing through the apparatus, which in my opinion, I think is kind of important to understand how that works. So I want to use this power supply to control that pump. Okay? So this is where everything starts. And so here is the control signal output here. I'm going to plug it into the hot side of this multimeter. Then what I want to do is take it through a level switch. So this is another component here. It's called a level switch. And basically it's like a little relay inside there. And as long as this float is down, the connection is closed and you can get energy flowing through it, current flowing through it. If the water level gets too high, this float will move up, and then when it moves up, it cuts off the electrical signal going to the pump. So it's a safety device. So I have to go through the level switch. So here we go. Level switch, level switch. So it's kind of a pass through. So I'm going to run the control signal through the level switch. So it comes out of the level switch, and then it needs to go to the control valve. CV signal here. And then the signal coming back goes back into the power supply there. So it makes a complete loop. So that's something about 4 to 20 milliamp. It forms this loop, okay? So you have to have some kind of power to run the loop, and then it has to flow all the way through the system and then back to the power source. So I'm going to go ahead and turn this on. I already have this bottom one provides power for that pump to operate. The valve inside can't turn unless it's powered. So it has a DC power. So basically once this is on, you don't need to touch it. It's just this one that you'll manipulate, the control signal. And so if I did everything right, so you can see I'm sending roughly 5.8 milliamps to the control valve, and I'm getting a little less than 3 liters per minute. Okay. So one of the things you're going to do in this lab experiment, I'm going to leave it like this for a second, see if my level switch works. You got to be very careful with this. So even though there's a level switch on there that should work, maybe it doesn't for some reason. Maybe you don't wire it up properly or something like that, or maybe it's defective. So you got to be careful. Whenever you're operating, and you'll have, and I'll explain this to you guys later, I'm thinking around maybe 26 is going to be the operating level. Now watch this signal right here. I'm going to be, just in case. So as the float goes up, that signal should go down. There it is. So that's how it works. So now basically it's kind of like an on-off type of control, but it protects us from overflowing the tank. Okay? So that's part of what you guys are going to do. You're also going to calibrate. Now this level sensor roughly matches up with what it says here. When you come in, this display isn't going to look like this, and I will talk more about that in a second. Okay? So that's kind of the basic idea for all the experiments, is that I want you to characterize or calibrate the input sensor, and I want you to determine the capabilities of the final control element, okay, for this part of the lab. This is a signal conditioner, and what it does is, so something about these controllers that's interesting, this type of controller accepts multiple types of input. So you can have a thermocouple input, you can have a process input, like 0 to 100 millivolt input. But for the process dynamics part of this experiment, we have to monitor the input signal and the output signal. And this controller is very difficult to get information out of. So I wrote a program in Visual Basic last semester to extract the input signal data, but I couldn't get the output signal data, so that's a problem. So I said, well, we'll just use a data logger that's easy to communicate and it has both signals, which is fine. And this can accept a wide variety of signals as well. The problem is they both have to be the same signal, so they both have to be 4 to 20 milliamp. So that's why this guy's here. I haven't programmed him yet, so I don't have him on yet. But basically, it is going to take that 0 to 100 millivolt output from the DP sensor and translate that into 4 to 20 milliamp signal. And we'll monitor both signals here, and it will store the data on the computer. Okay? So you'll see that this theme is going to be kind of repeated through the different experiments. So that's level control. And the other level control station is going to work essentially the same. The only thing is it's not going to have one of these transmitters because I'm only going to set up 3 stations that have the data loggers, because I don't want to buy a whole bunch of data loggers and find out that they don't work so well and pay. Those 3 of them is about $1,200. So Dr. Ma gave me $8,000 to build stuff in the process control lab this semester, so I'm very thankful for that. And these are the last things I got to buy. So, anyways.